Rensa is a Swedish word which means clean in English. Rensa is a high performance min hash implementation written in Rust language with Python bindings. In simple words, Rensa is used for finding similar items in large datasets, which is useful when preparing data for training or fine tuning models. Now, if you have worked with data sets, one of the biggest problems with these data sets is the repetition or duplication. If you want to deduplicate the rows or records in a data set, it is quite a big task. It takes a lot of time, lot of manual custom programming, and even then you're not really sure if your data set is free of duplicates. That is where this min hash comes into play. Rensa implements a variant of the min-hash algorithm that combines ideas from traditional min-hash and the C-min-hash algorithm, which was proposed in a very famous paper called as min-hash rigorously reducing k permutations to 2. It is used, and I mean Rensa, to create a novel min-hash implementation that you can call as R min-hash or Rensa min-hash. Rensa is really useful in scenarios where you need to quickly estimate the similarity between large sets of data. You want to deduplicate large data sets, or you perform locality sensitive hashing or LSH for approximate nearest neighbor search. And there could be a lot of use cases. For example, you could do content deduplication in large document collections. You could identify similar items in recommendation systems, and you can make it part of your RAG pipeline. You could do clustering of high dimensional data, or you could do near duplicate detection in web crawling. There is a lot of great detail about its technical implementation in this GitHub repo, and I'm going to drop the link to it in video's description. Before we install it locally and see how it works, let me give a huge shout out to Massed Compute who are sponsoring the VM and GPU for this video. If you're looking to rent a GPU on cheap prices, I will drop the link to their website and a coupon code for 50% discount on range of GPUs, so do check them out. The VM I'm going to use for this demo is this Ubuntu 22.04, and the GPU card I mean, is this NVIDIA-SMI. You don't really need a GPU card for this demo, but if you're looking to do that, or if you're looking to implement a RAG pipeline, then it would make a lot of sense. Okay, and I'm just going to create a Conda virtual environment where I will keep everything nice and simple. If you don't know what Conda is and how to install it, then okay, so I'm logged in as root by the way, so I'm just going to exit, clear my screen and do it again. It is going to create the virtual environment and then activate the virtual environment. Let's wait for it. And that is done. Let me go to home directory, clear the screen. And in order to install Rensa, all you need to do is to do pip install Rensa, and it is going to install the Rensa on local system very quickly. It's all done and set. Let me fire up my Python interpreter. In this demo, after installing the Rensa, what we are going to do, we are going to load our data set, and then from there we are simply going to do the deduplication from that data set. So let me first import some of the libraries, and I have imported the data set and then tqdm and Rensa, and they should already be installed in your system. If not, simply do pip install datasets and pip install tqdm. Okay, so now libraries are imported. Let's define the Rensa Minhash function. It's a simple math function from their GitHub repo, which I'm using, which is receiving a text and also number of permutations. That is done. And let's define a function for deduplicating the data set, which is going to return the indexes. So it is simple, again, Python function, which is receiving the data set, number of permutation, and then it is going to convert it into hashes. And I'm also going to describe these technical details shortly. Let me first show you. Let's download the model, data set I mean, by using this main function. As you can see, for the purpose of this demo, we are just downloading this gretlai synthetic text to SQL, and then simply you can run your main function here. It is loading the data set. You can see here, and now it is deduplicating, and there are 100,000 rows, and look at the speed. And then it is going to give us some of the deduplication results, and how much was original size, and then how many were duplicated. There you go. So original data set size was 100,000. Deduplicated data set was this, and this many rows were removed from your data set. So if you think about it, you can easily utilize this thing with any of your data set, and you can just do it for free, quick, you know, without any without using any large language model or stuff like that. Now coming back to this deduplication set, I just wanted to go a bit more deeper into this technical detail, especially around this permutation. So the Rensa's implementation includes this efficient permutation generation. So instead of storing full permutations or using k-independent hash functions, Rensa uses a pair of random numbers, A and B, to generate permutations on the fly. This approach significantly reduces memory usage while maintaining the algorithm's effectiveness. Also, Rensa implementation differs from the simplified C-min hash in couple of terms. First, it does not apply an initial independent permutations to the input data, and instead of using circulant permutations for each hash value, Rensa uses the same pair of random numbers. Also, Rensa's approach trades some of the variance reduction benefits of full C-min hash for improved memory efficiency and simplicity. And while it may not achieve the same level of variance reduction as C-min hash, it still offers better performance than traditional min hash in many scenarios. Also, Rensa uses the Rust C hash grade, which implements the FX hash algorithm, that is a fast, non-cryptographic hash function to further optimize performance. Also, the R min hash computation is optimized using a vector operation that allows for efficient parallel processing of multiple hash values. And the implementation uses compact data structure to minimize memory usage while maintaining fast access time. And there are a lot of great things which are happening in this one. I know this is a bit boring if I go into math details, such as another LSH implementation, so I'm not going to bore you with that. But I just want to tell you that these design choices result in a min hash implementation that is fast, memory efficient, and suitable for large scale similarity estimation and deduplication tasks. And I think that is where this Rensa make a lot of sense, and I can envision that it could be part of any RAG pipeline or even your dataset preparation pipelines. Because while Rensa may not provide the same theoretical guarantees as full C-min hash, but the benchmarks show that it offers significant performance improvement over traditional min hash implementations like Datasets. So that's it, guys. I hope that you enjoyed it. Let me know what do you think. You can find all of these commands in this GitHub repo. I will drop the link to it in video description. If you like the content, please consider subscribing to the channel. And if you're already subscribed, please share it among your network as it helps. Thanks for watching.